We're going to continue talking about buffers. And the amounts of acid and base are one factor that influences how effective a buffer is. And it's really the relative amounts of acid and base. So a buffer will be most effective. It's bolded, but I guess I'll highlight it anyway. Buffer's most effective when the concentration of acid and conjugate base are equal. So let's compare 2 1-liter solutions of a generic buffer. pKa is 5. And we're going to calculate the percent change in pH when we add 0.01 moles of sodium hydroxide. So it's kind of set up here for us to save a little time. We've got a 1 liter of buffer, so it's 0.1 moles of HA, 0.1 moles of A minus. We're adding hydroxide. So this is our MICMA table. If anybody can come up with a better name for that, please let me know. We can change up these words as long as it has the same meaning. So hydroxide, and that's going to react with the acid in the buffer to produce water in the conjugate base. So the initial moles of hydroxide is what's being added, and that was explained on the previous slide. We're adding 0.01 moles. We had 0.1 moles of HA, 0.1 moles of A minus. So in the change, we're looking at which of these is the smaller. It's the 0.01. So that's going to react completely to give us approximately 0. And so that's minus 0.01. So this one is also minus 0.01. That one is plus 0.01. And so 0.1 plus 0.01 is 0.11. Okay, we're doing this in moles, not in molarity. Any questions about how we fill out that table? Because that's something new in this chapter. So we need this table because this is going to help us, this is going to give us our initial values for doing a pH calculation. So the initial pH of this solution was 5. Remember, there's 2 ways we can find the pH of a buffer. We can use the Henderson-Hasselbalch equation, which works when x is small, or we can do the full equilibrium. Let me see, what am I missing here? What do we need to do either calculation of the pH? We need the pKa. It doesn't give the pKa anywhere. On the previous page it says it's 5? Oh, good. If it didn't say on the page, we could get it from here. When the concentrations of acid and conjugate base are equal, then the pH is equal to the pKa. And we get that from the Henderson-Hasselbalch equation. If the concentration of the base is equal to the concentration of acid, this fraction is 1. The log of 1 is 0. pH equals pKa. So that's how we get the pKa if we didn't see it on the previous page. So pH is 5.0 plus the log. We want to use molarity here. You don't always have to use molarity, but it's just safer. So using molarity, this is the moles, and it was a 1 liter solution, so it's the same number, right? So the HA is 0.09 molar, and the A minus is 0.110 molar. Everybody see where I got those numbers? So we can calculate the pH. It's going to be 5 plus the log of 0.11 divided by 0.09. 5.0872. And what they wanted us to find was the percent change. Oops. Having some technical issues here. I didn't leave enough space. So percent change would be the difference between the two divided by the original value. So percent change will equal our final pH, 5.0872, minus our initial pH, 5.0, divided by the initial pH, times 100. When you have percent errors and percent changes, looking at the sig figs can get a little bit ugly because you've got subtraction and division and multiplication in here. So with percent change, percent error, 2 sig figs is usually plenty. So I'm just going to report 2 sig figs, 1.7%. So that buffer had a 1.7% change. Everybody okay with that? You guys awake? Yeah? Well, half of you. That's okay. So let's look at this other one. Here we've got 0.18 moles of HA and 0.2 moles of A minus. And again, we're adding 0.01 moles of hydroxide. The initial pH of this one is going to be a little different, even though it's the same acid, because the initial ratio of base to acid is a little different. So we make our MICMA table here, and 0.01 is the smallest again, so we're going to react all of that. This goes down by 0.01, this goes down by 0.01, that goes up by 0.01. We add them, and that gives us the moles of our acid and conjugate base for our ice table or for our Henderson-Hasselbalch equation. And again, we want to do that in molarity. It was 1 liter of solution, so the moles and the molarity are the same. So the pH is going to equal the pKa, which is still 5. This was different than 5 again because this ratio was different. So 5 plus the log of the base concentration. So here's our base. We've got 0.03 moles in 1 liter. So that's 0.030 moles per liter. And our acid is 0.170 moles or 0.170 moles per liter. So the new pH is 4.2467. So to find the percent change, we're going to use our final minus the initial. The initial here was 4.05. I don't know how that happened. Divide by the initial times 100. So that's going to be 4.9%. In this buffer, we had equal amounts of acid and base. When we added the sodium hydroxide, we had a 1.7% change. Here, we had significantly more acid than base, and so the initial pH was a little different. And when we add base to that, we get a 4.9% change. So your best buffering is going to happen when you have equal amounts. Any questions? Well, of course, it's not always going to be equal amounts. The range where it's reasonably effective is where the ratio of base to acid is between 0.1 and 10. So that means the base and the acid, one is no more than 10 times bigger than the other one. If that's the case, then you've got a reasonably effective buffer. Let's look at this guy. Are these different by more than a factor of 10? They are, right? 0.02 times 10. Oh no, actually, they're okay. If I multiply this by 10, I get 0.2, which is actually bigger than that. Or we could look at 0.020 divided by 0.180. And that's, well, make it into no, we need the fraction, never mind, 0.11. So we want that to be greater than 0.1 and less than 10. So that does make it into a reasonably effective buffer, just barely. Any questions? So the relative concentrations matter. The absolute concentrations also matter in the effectiveness of the buffer. So a buffer will be most effective when the concentrations of the acid and conjugate base are high. We want the ratio to be roughly equal, and we want the concentrations to be high. So again, we're going to look at that same generic buffer, but now we're going to look at solution 1 having concentrations 10 times larger than solution 2, and again, we're going to calculate the pH, the percent pH change. So for both of these, we have equal amounts of acid and base, right? And so that's optimum for buffer effectiveness. Here it's 0.5 moles of each. Here it's 0.05 moles of each. So we make the MICMA table. Again, we're adding 0.010 moles of hydroxide. So the equation we're going to put here is hydroxide plus, it's going to react with the HA to make the A minus. And then we'll put in the moles of each of these that we have to start with. We look at this. This is the smallest one, so this will go down by that amount. This will go up by that amount, and we get these values. So we're going to use the Henderson-Hasselbalch equation again. It's very rare that you can't use this for a buffer solution. But if you don't like the equation, you could always do the equilibrium problem. So pH is going to equal the pKa, which is still 5, plus log of the base, 0.510 moles in a 1 liter buffer is 0.51 molar. This is 0.49. So a new pH is 5.0174. Percent change, 5.10174 minus 5 divided by 5 times 100. .35%. A very small change. Did you follow what I did there? Same process as on the previous page. So here, we just have different starting amounts, but the process is the same. So we're going to subtract and get our new initial moles of acid and base, which we then can convert into a concentration. The pKa is still 5. And now the base is 0.060 moles in 1 liter, so that's 0.060 molar, and the acid is 0.040. New pH 5.1761. Percent change. .5%. The concentrations here were 10 times larger than over here. And then the percent change happened to be 10 times less. So 0.35% instead of 3.5%. So, good buffer, we want relatively equal concentrations of acid and base, differing by less than a factor of 10, and we want higher concentrations rather than lower. So we can calculate the outermost points of the effective pH range of a buffer. So, the lowest pH where it will be effective is when the base is 0.1 times the amount of acid. And the highest pH where it will be effective is where the base is 10 times the acid. So if we put this in, so the base is equal to 0.1 acid, so I'm going to put that in instead of base concentration, divided by the acid concentration. And so this gives us pKa plus 1. Wait, minus 1? I better do the math. Is minus. pKa minus 1. Here, oops, plus log. The base is 10 times the acid. Any questions? We're just kind of demonstrating where some of these guidelines come from. So the effective range for a buffering system is 1 pH unit on either side of whatever the pKa is. So if you need a buffer of a certain pH, there are different weak acids and weak bases that you can choose from to make that buffer. It will be most effective when the pH is equal to the pKa. But there might not be a buffer system available that's exactly right. So then you want to get one where the pKa of that system is going to be close to the pH, right? Closer is better, but it definitely needs to be within 1 pH unit of the pKa. We can adjust the pH of the actual solution by altering this ratio. But we don't want to have to change it too much. Okay, so we need to make a buffer with a pH of 7.35, and it's asking which acid would we choose. So these are 4 weak acids, and we're going to choose one of them, and that'll be the acid, and then we'll use the sodium salt as the conjugate base. So if we want a pH of 7.35, what kind of a pKa are we looking for? Yeah, as close as possible. So here we've got a bunch of 3s and a 7. So it's kind of clear that we want that last one. So remember, HClO is going to ionize. It's a weak acid, right? And it's going to make hydrogen ion and hypochlorite ion. This is the acid, and so then we need to add the conjugate base as well. This is the conjugate base, but that can't just be by itself. It has to have a counter ion. So that's what this is saying here. We're going to use the sodium salt. So this with a counter ion of sodium. Sodium hypochlorite. Okay. This part about the sodium salt and being able to figure out what that is, that's something you just need to know how to do. They're not always going to tell you this is the formula of the base that we're adding. Okay. Any questions about that? So if we have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? Well, what are we doing here? We want the pH to be 7.35, right? We can start out using the Henderson-Hasselbalch equation. To figure this out. So the pH that we want is 7.35. The pKa for this acid is 7.54. Okay? Plus the log of these two concentrations. Well, we're given information about the acid. The acid concentration is 0.1. So I can put that in for the acid concentration. And then the base concentration is what I'm solving for. Does that make sense? So we've used the Henderson-Hasselbalch equation when we know the composition and we're going to calculate the pH. Now we're trying to get a certain pH and we can use it to calculate what the composition needs to be for it to have that pH. So depending on your relationship with math, you may just kind of rearrange and solve this in your head, or you could use the solver, right? So I'm not going to go through this in detail, but what I'm doing in my head as I solve this is I'm taking the 7.35, I'm subtracting the 7.54 from that. And so that's giving me negative 0.19 equals the log of base divided by 0.1. To get rid of the log, I do 10 to the x of both sides. So log of both sides, and I get 0.6457 over here, and base over 0.1 over there. And so I multiply this guy by 0.1, and my base concentration should be 0.06457. Anybody else come up with that value? Okay, good. Okay, so that's great. This is the molarity we need. And this is where a 1B problem gets a little more practical. How much sodium hypochlorite do we need to add to get that? This is a Chem 1A problem. Okay, so this is the molarity we need, moles per liter, and we're given a volume, so we know what the volume of the solution is, and we know the formula for the sodium salt that we're adding. So we're using this number and this number, and we can think of this as dimensional analysis. This is a single unit, milliliters. It might be helpful to rewrite this as moles per liter. That's something that kind of slips your mind sometimes. This is moles per liter. So sometimes it's like, well, which number do I start with? Well, start with the one that just has a single unit, because this is probably going to be a conversion factor. That one is not, right? So I'm going to start with that one. Let's change color here so things don't get too mixed up. I think it'll fit down here. So 500 milliliters is how many liters? 0.5. It's great to be able to do those conversions in your head. It's bad if you do them backwards, right? So 500 milliliters is not 500,000 liters, right? You can check this. This is the small unit. It should have the big number. The big unit should have the small number. That'll tell you if you went in the right direction. So 0.5 liters, and then I'm going to use this as my conversion factor because I want moles. So I'll put liters down here. And then I need to get to grams, right? So over here, I'm going to have another conversion factor with grams over moles. It's a review of dimensional analysis. Put all the units in first, and then that's going to tell you where to put the numbers. So moles per liter, this one is moles per liter, so we're just going to put it in like this, and of course I didn't leave enough space. It's okay, we can squeeze it in. And then we need, this would be the molar mass of sodium hypochlorite, right? So sodium is 22.99, chlorine is 35.45, oxygen is 16.00, 74.44 grams per mole. Now I do the math. Just start at the left and go left to right. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. That way you're not gathering things up and having a denominator and a numerator and having to, do that division and type things in extra. I just go straight across. So 0.5 times 0.06457 times 74.44. So this is going to give us 2.403 grams. We're working with two sig figs. so 2.4 grams. If you wrote 3 sig figs, that's fine. The pKa's are log numbers, and so it's only the decimal places that count. So there's 2 sig figs here. Also, when we subtract these, we end up with 2 decimal places, which is 2 sig figs. Any questions? So a common mistake that a student might make here is when they're doing the molar mass of the base, they might forget about the sodium. Because you're like, oh, well, I just need this many moles of ClO minus. But you can't get it by itself. It comes with the sodium. Okay, so just watch out for that one. Any questions? So we're talking about buffer effectiveness. The buffer capacity is how much acid or base you can add without causing a large pH change. The amount that you can add will increase with increasing absolute concentrations. The more concentrated your buffer is, the more acid or base it can absorb. It will also increase as the relative concentrations become closer to equal. If we have a buffer that's going to mostly need to neutralize acid, then we'd like that buffer to be a little heavier on the conjugate base side. If it's going to have to neutralize base, then we'd like it to have a little more of the acid. So a concentrated buffer is going to have more weak acid and more conjugate base species than a dilute buffer, and so it's going to be able to neutralize more. Does that make sense? A 1 liter buffer solution is 0.1 molar in HF and 0.05 molar in NaF, which action destroys the buffer. Adding 0.05 moles of these different things, HCl, NaOH, or NaF, or none of the above. Always scary. This is conceptual. We're not supposed to do a whole calculation. So we have to think about, well, what's going to happen here? If we add 0.05 moles of HCl, what's the important thing that we're adding there? Acid. We're adding H+, so we can ignore the chlorine. So if we're adding 0.05 moles of H+, is that going to react with the HF or the NaF? It'll react with the NaF. That's the same amount in a 1 liter buffer. If we have 1 liter of this buffer, that's 0.05 moles of NaF. If we add an equal amount of HCl, that's going to use up all of the conjugate base, right? Do we have a buffer anymore? No, we don't. So that's probably the answer. But we got to check the other things anyway. What if we add 0.05 moles of sodium hydroxide? What do we care about here, the sodium or the hydroxide? The hydroxide. And what's that going to react with, HF or NaF? It'll react with the HF. So 1 liter of this is 0.1 moles of HF, and if we add 0.05 moles of sodium hydroxide, that's going to take out half of it, right? But we've still got some left. So it would still function as a buffer. So this is not going to destroy it. If we add 0.05 moles of NaF, this is one of the components of the buffer. So we currently have less NaF than HF. So if we add more of this, is that going to make the buffer better or worse? It's going to make it better. So it's definitely not going to destroy it. And so then obviously none of the above doesn't work because A was correct. Any questions?